Okay, we're going to continue to explore the relationship between matrices and linear functions by looking at matrix multiplication. And let me just give you the punchline here, is if you have the composition, now you know what composition is. Composition of linear functions is equivalent to multiplication of matrices. Okay, so we know that linear functions are represented by matrices, and if I want to compose two linear functions, that is, I apply one function first and then the second function, that's the same thing as multiplying the matrices associated with the two linear functions. Right, so that's the punchline, that we'll see the details unfold in the subsequent slides. Okay. All right, another function operation besides scalar multiplication and addition is composition. Okay. Composition of linear maps is linear. Okay, let's get the proof. So here we have one map followed by another. So here we have spaces V, W, and U. And here we have the map H from V to W, and we have another map G from W to U. And we do the calculation G composed H. Now this means G following H. You do H first and then G. And it's a little confusing because the order seems to be reversed, but that makes sense. This is like G of H of C1V1 plus C2V2. Okay, to prove linearity of G composed H, all we have to do is show that G composed H of a linear combination is the same linear combination of G composed H applied to the individual vectors. So you can see that where we're trying to get to is exactly here. Let's follow the intermediate steps. Well, you're like unpeeling in two different steps. First of all, you know that G composed H is the same as G of H. And we can apply linearity of H to take this H of this linear combination as a linear combination of the H's. Right? Now we have G of a linear combination, and since G is linear, we can take the linear combination outside. And then we make the identification of G of H with G composed H. Okay, so what we've done is show that G composed H is linear. Okay, by making use of the properties of G and H separately being linear. All right, so let's do an exploratory calculation to see how the matrix representations of two functions combine to make the matrix representation of their composition. So, like the punchline I already shared, we're going to see that this corresponds to matrix multiplication. All right, let's take an example of two linear functions. F goes from V to W, and G goes from W to X, represented here. Now, first, H goes from V to W. Question, what's the dimension of V? Well, to get H of any vector, you multiply the matrix by the representation of the vector. So we can see that the representation is two-dimensional. So the dimension of V is equal to 2. Now, when you multiply this matrix by a two-dimensional representation, you're going to get a three-dimensional vector. So the dimension of W is equal to 3. All right. Now we're going from W to X. We know the dimension of W is 3. And that corresponds to the fact that this 2 by 3 matrix should be multiplied by three-dimensional vectors. But the result is going to be a two-dimensional vector. So the dimension of X is going to be 2 again. Okay, so that's how we get these results here. we want to show how these two matrices combine to represent the map G composed H. Okay. First, we represent the action of H on a vector V. Okay, again, the usual way to get the action of H on V, we express the vector V in terms of the basis B. And here's our representation of H in terms of the bases B and C. Matrix multiplication determines the representation of H of V with respect to the codomain basis. All right. In this, notice that B is a basis in V, so B is contained in V, and C is a basis in W. B is the domain basis, C is the codomain basis. Okay. So this gives us the representation in basis C of H of V. Now I think you can see what the strategy is. In order to get the representation of G composed H, we're going to apply this matrix here to this representation. And that's exactly what we do. If you remember this matrix here is the same as this matrix here. And this vector here is the same as this vector here. Okay. Multiply them together and you get this result. And now we want to unpack this. If you gather the terms, they look like this. All the V1 terms in the first component, all the V2 terms in the first component, all the V1 terms in the second component, V2 terms in the second component. And here you have this matrix style multiplication. You can verify that in fact this multiplication is the result of typical matrix multiplication. And this is how matrices were first discovered. I'm sorry, how matrix multiplication was first discovered. It's not just an arbitrary rule. It actually corresponds to a mathematical operation of composition. Okay, so if we just want to define this operation in terms of the arithmetic, the ij entry of the product is expressed in this way. Now notice that G is the first matrix and H is the second matrix. So we have GI1, GI2, GIR. And those are all the entries in the ith row of G. Similarly, we have H1J, H2J, and so on. Those are all the entries in the jth column of H. And we pair these up one by one, multiply, and add together. And where you put that result is exactly in the ith row and jth column of the product. Okay, example here, for example, if I want the second row, second column entry, it's 2 times 0 plus 5 times minus 3 gives me minus 15, plus 9 times 2, which is 18, minus 15 plus 18 equals 3. That gives me the result right here, second row, second column. In this case, the product is not defined because when you do matrix product, you take the product of each row with each column. And the row and the column need to have the same number of entries. So here if we have m by n, and here if we have, say, r by s. In order to do multiplication, you need n to be equal to r. If they're not equal, then a multiplication is not possible. Okay, they have to be equal for multiplication to be possible. Okay, square matrices of the same size have a product because the number of columns of the first will be equal to the number of rows of the second. Okay, and you can do, again, a sample multiplication here. For instance, first row times second column is going to be 7 plus 6 gives me 13 plus 1, 14. That should go in the first row, second column of the result, and it works. right? The fact that you can multiply matrices reflects the fact that you can always compose functions from a space to itself. If F maps V to V, then I can apply G to the result because G also maps V to V. Now, matrix multiplication represents composition. Composition of linear maps is represented by the matrix product of their representatives. We showed that for a particular example above, and now we state the proof. Okay, let's consider two linear functions represented by matrices H and G respectively. We specify the bases B and V, C and W, D and X. So remember this picture, here's V, W, X. And this is the map. The first one is H, and the second one is G. Okay. Now, for any vector V in the original domain, the kth component of its representative with respect to so here, let me put the bases under here. C is here. I'm sorry. B is here. C is here. D is here. So we want the representation of H of V, which lives in here, with respect to basis C, which is the basis of W. Okay. And we know already that this is obtained by matrix vector multiplication. So this is the kth row of matrix H multiplied by the column vector of components of V. Right? So from this we want to get the component of the representation with respect to the D basis of G composed H. So what we're doing is we're taking the ith component that corresponds to the ith row of G. So here's the ith row of G. And what we want to do is multiply GI1 times the first component of this representation. Okay, so we're taking GI1 times the first component. First component is this expression here with k equals 1. If you take this expression and replace k with 1, you'll get exactly this expression here. Okay. This is the expression up here with k equals 2. Here's the expression with k equals r. Okay. So we're doing the same thing we did up here, only this time, instead of taking the components of V, we're taking the components of H of V in its representation in the C basis. Okay. Then you do some regrouping. Group all the terms that are associated with V1, and group all the terms that are associated with V2, and so on. And this is what you get. Now notice here we have matrix multiplication right away. Here, this is the I1 entry of the product of G and H. This one here is the IN entry of the product of G and H. So you can see already that we do have matrix multiplication. Okay. Recognize that the coefficient of each Vj, here's row I, column j, first entry, row I, column j, etc., etc., etc. We have the ij entry of the product gh. And the proof is complete. All right, these arrow diagrams are very useful to see the relationship between the maps and the matrices. Okay, so here we have the vector space V, and if you just consider the vector space V, there's a linear map from V to H, or V to W rather. Now, if you consider V with respect to the basis B, then that basis B and the basis C in W are going to determine a unique matrix H corresponding to this linear map H. We can do the same thing on this side. W maps to X via the linear map G. But if we choose a specific basis C and D, and that gives us a specific matrix G that represents the map little g. Now this final side says that if I go here first and then here, that defines a map from V all the way to X. The map defined via H and G is G composed H. And it turns out that the matrix corresponding to that composition map is just the matrix product of big G times big H. Okay. All right, so this recaps what I said. The map shows two ways of getting from V to X, straight over by a composition or else in two steps. You get the same effect both ways. You either go directly to G composed H or you can go by steps. In fact, this is defined by this process. Okay. Below the arrows, the matrix indicate that multiplying GH into the column vector rep B of V has the same effect as multiplying the column vector first by H and then by G. Okay. So the representation of the composition is GH, and also the GH is equal to the product of the representations. Okay, so let's look at implications with order, dimension, and sizes. Consider the composition of two functions. Okay. Consider first the order in which we write the composition. In G composed H, the function written first, G, is the function applied second. I already referred to this. This is G of H. You take H first and then G. Okay. This order carries over to matrices. G composed H is represented by the matrix G multiplied by H. Okay, so in fact, you're applying H to the vector. Remember, the vector is written on the right. You apply H to the vector first, and then you apply G. Next, consider dimensions of the domain and codomain. Okay, so if you have a dimension n space that's mapped to a dimension r space by H, and a dimension r space that's mapped to a dimension m space by G, if I'm going from dimension n to dimension m, that's a m by n matrix. All right. Now, we know that we can get from this domain to the final codomain by multiplying two matrices, the matrix for this little h and the matrix for this little g. Now, what's the dimension of the matrix associated with little h? Well, it's r by n. What's the dimension of the matrix multiplied associated with little g? Well, it's m by r. Now remember, you put this matrix first, this matrix second. So what we get is a m by r times a r by n gives me the result, which is a m by n matrix associated with the map from dimension n to dimension m. Matrix multiplication is not commutative. This should not be surprising because function composition is not commutative. For instance, if I take the squared function and the cosine function, if I square first then take the cosine, that's quite different from taking the cosine first and then squaring. And this holds even in the special case of composition of linear functions. And we see that in matrix multiplication. We can multiply two matrices this way or this way, and you get a different result. Okay, the product of these matrices is only defined if you take this matrix times this matrix. It's not even defined if you multiply it in the other order. Okay, so remember, matrix multiplication is not commutative. Okay, nonetheless, matrix multiplication has nice algebraic properties. Okay. In fact, matrix multiplication is associative and distributive. Okay, and these are the standard properties of operations that you've seen in ordinary arithmetic. Okay. So here the multiplication distributes over addition, and multiplication associates. Okay, associativity holds because matrix multiplication represents function composition, which is associative. Okay, so whatever is true for function composition must also be true for matrix multiplication. Distributivity is similar, okay, because you also have distributivity of linear functions. Okay, and you can distribute on both sides. All right, let me stop here and we'll pick it up with the next video.